Good evening all, 7:30, let's get started. So tonight our topic was the parallel processing part 3, parallel processing architecture, and this is the last part of this module, and possibly we'll conclude with this processor design and architecture related to the processors in this module, and then next time we'll start on the um, memory hierarchies, memory systems from the next week, which is another important part of the computing system, and it helps to make uh, faster computing system as well. Not only processor improvement is needed for a faster processor experience, but associated with that memory system needs to be upgraded and as well. So that is the whole topic, and we'll try to understand in rest of the semester from next classes onward is how the memory system affects and what are the different nomenclature and hierarchy available in a computing system memory and how it impacts the performance of running a program. So any question for so far in the from the processor side, like parallel processing architecture and those side?
This is not about the parallel processing, but it's about the previous module.
Sure, no problem. Ask me.
Okay, so for the B and E and BEQ instructions, there's a control hazard there. So so after the B and E, you have to wait until after the EXC phase is over, and to know whether the branch is taken or not taken. So from there, uh, I saw in the video that you had to do two instructions could have executed in the time before the end of the EXC phase of the branch instruction. So like after, so if B and E is instruction 2, then instruction 3 would be fetched, and then instruction 4 would be fetched, and then only only after like the end of the second instruction, which is the B and E, the end of the EXC for that, you would know the result. So would that mean that we abort both instruction 3 and instruction 4, and then we fetch an instruction 5 at that stage too?
Yes, yes, that's correct.
Okay.
So basically, what happens there is we know. Let's say our controller prediction was wrong, and then it will abort. It needs to abort those two instructions already in pipeline, and get one more into the pipeline at that point.
Yeah, because like in the video was kind of different. Like the instruction 3 was like abort was like halted, but then the instruction 4, the instruction 4 was it was like it was not it was just kept there. So I thought it would
I know,
be.
like that is little bit confusing, but please follow the one I explained in the class last time with that five stage cycle,
Uh-huh.
and at what point we are getting instruction and what point it is being aborted. That is like should be uh, much clearer explanation of that whole thing. Yeah.
Okay, so to summarize, like after the B and E instruction, 2 more instructions get fetched, but after the end of the EXE cycle, if the branch prediction is wrong, then we stop those two, stop the third and fourth instruction, and then also at the end of the EXE or the beginning of the mem, we also begin an instruction fetch there too.
Yeah, so that instruction fetch is automatic, right? That instruction fetch, we are always doing instruction fetch in every clock cycle, doing
Okay.
instruction fetch.
Okay.
The question is which instruction to fetch. So
Yeah.
only after the execution of the BNE instruction, when it goes past the EXE stage, then only controller knows for sure which instruction to fetch. So accordingly, that it basically instruct memory to fetch from each location.
Yeah, so after the BNE EXE phase, right after that, the new instruction gets fetched, but that instruction is now the instruction with the correct branch, like the correct branch prediction.
Right, right.
Okay, thank you.
Okay. So if there is no other question, just I'd like to point out two important aspects of this lecture 18. One is that cluster computing. Cluster computing philosophy is like this, like in early days, like this SMP, symmetric multiprocess system, was dominant in the market, which means a bigger motherboard with a lot of components in it, and it's a big server we are talking of there in the data center, or even data center concept was not there at that much distinction. But something like when like companies, industries, storage server, or processing or compute farm is established. They have these big machines, big SMPs with big memories and all this stuff. And those machines tends to be very high pricey machine. So that's when industries start thinking, at least a group of people start thinking that how can we turn around the priciness, where basically like there are cheaper machines, lower in performance, like they are smaller machine like a desktop, for example, but it is cheap. Then can we somehow connect them together to build up a system which gives us superior compute performance? So that is the whole rise of this cluster computing. And people try to save money on budgets, the industry scale, and they want to grab this smaller, cheaper machine and somehow build a compute farm or compute ranch, which is superior in performance. And there it comes that involvement of the network communication. So so this smaller computer needs to have these ability to communicate with each other, talk with each other. And since they are not even sharing one common motherboard, it is going through the network route. So basically, and luckily, at that point of time, network communications are also growing up and it's also evolving to a point where people can actually combine these two together into a build up a compute farm, compute ranch, whatever you want to call it, and build up this cluster computing environment with the using the smaller machine. The philosophy, programming philosophy there, like from if you are trying to think from a programmer perspective, your job is to define your algorithm and implement in such a way you tear down your problem in smaller subset of the problem and then send subset of the problem to each of this compute node, get the solution done, and then combine the solution from the each subset set of the problem set, combine them into the final result. So that is the basic philosophy of the cluster computing. So you practically try to grab resource from the compute range, and you get, let's say, 10 machine or 20 machine. Depending on that, you divide your problem into subset of problem. For example, let's take about like some matrix multiplication problem, right? So that is one classic example that you can think of from software perspective, that you can actually big matrix multiplication, you can chunk it up into smaller matrix multiplication problem and combine at the final step the result to give your final multiplication matrix multiplication result. And I mentioned the matrix multiplication because matrix multiplication is a very unique problem that is applied across many different domains. For example, graphics manipulation. If you took the graphics classes, like core theory is practically your image processing is nothing but a matrix manipulations at a very, very crude sense. Simulation, like simulation of real-time system, electronic simulations, those are all huge underlying main mathematical engine is the matrix manipulation, matrix calculation. So this is very important problem, and cluster system is very ideal, suitable for that type of parallelization of the problem. Like you can divide it into subset of the problem and send it to the compute node. Only thing you need to concerned about there is the memory usage. You are limited to use the memory of that local node that where your subset of the problem is being executed. Okay, so so you cannot, even if like your cluster has like 1000 node, and let's say each node is one machine, let's say, and each such node has, let's say, 10 gigabyte of memory, then practically you kind of have 10,000 gigabyte memory in your hand in your cluster computing environment. But your one process which is deployed in one single node can only access that 10 GB, like assuming that is yours is the only process running there. That is the one limitation for the cluster computing environment. Whereas SMP, if you look at the symmetric multiprocessing system, though it is limited number of processors there on the single motherboard, but all the processor enjoys the big combined memory together attached to that motherboard, attached to the system. NUMA is somewhat in between those two architectures. That's where it evolved. That is said, it's the cluster computing. There are nodes, but the machines and systems are upgraded such a way that one process in one node can actually access memory which belongs to the other node or other machine. So it's all like through the network communication, it basically can access the other node's memory. That means you no longer limit to that single node's memory that your subset of the problem is being executed, but that subset can actually access the other part of the memory if it needs it. So you're no longer bounded by the individual machine's memory limitation in the NUMA system. So that is the advantage, and that is the midpoint where the NUMA architecture is gaining traction. And regarding that, why don't we do a performance problem, which is something like this. Let me share my screen with you. Okay. So here's the problem. Here's my problem. Here's this. There is a NUMA cluster, has 200 computing node. We have 200 computing node. And with each node associated with 120 gigabyte of RAM. The average local access time is 50 nanosecond. Is 50 nanosecond. And that means, like, let's say the subset of the problem that I was talking about, if it is running on a machine, it can have local memory access of maximum of 128 GB, which is 50 nanosecond time, let's say. And an average remote memory access is 180 nanoseconds. So if it is not accessing a local memory, it is accessing memory from the other node in the cluster, it will take 180 nanosecond in average for that accessing that memory. Now assume a program is running on one node on this cluster and it is consuming total 230 gigabyte memory with local memory occupancy 100 GB. So let's say out of 120 8 GB, 28 GB is given to the other processes, and 100, your process can grab only 100 GB. Now, if there are 1 million memory access in the program, with probability of accessing a remote memory location is 0.25, so 1/4 of the all memory access is remote memory access, then what's the total time of the program busy in accessing memory in the millisecond unit? So this problem, what we can do is this way. Let's say, so we are talking about, just hold on. Why my Jamboard is falling. Okay, all right. So you have, like, let's say, local memory access. There's a number of local memory access is 10 to the power 6 multiplied by 0.75, which is 750,000. And the remote memory access here is 25% probability, which is like 250,000. Right? That means the access time for the local memory, we all know it is this 50 nanosecond. So this is like 750,000 multiplied by 50 nanosecond, which is about, this is 10 to the power 4, 10 to the power 5. Okay. 375 multiplied by 10 to the power 5 nanosecond. And access time for the remote memory is 250,000 multiplied by 180 nanosecond, which is an average, which becomes like 10 to the power 5 and 25 multiplied by 80, which is, let me just use a calculator, 1, 2 multiplied by 25, 450. 450, 10 to the power 5 nanosecond. The total time for memory access would become like 375 plus 450, 10 to the power 5 nanosecond, which is about 825, 10 to the power 5 nanosecond, which is like 825, 10 to the power 2 microsecond, which is 82.5 milliseconds. If you are interested in conversion of the unit of the time, it's that 82.5 millisecond is your answer for this one. Question?
So the thing you said about the 230 gigabyte total memory with the local memory occupancy as 100 gigabytes. So does that play anything into getting the final answer, or is it just extra information?
So this is that's a good question. Let me see. Consume total of this thing. Yeah, this is first of all, this one is help you to determine, hey, my uh, I have some remote access. That's just to make sure that that part is okay, right? Other than that, it doesn't play much role there in this problem. Other than that, it doesn't, yeah, play much problem. Uh, Whereas if this type of problem can get like make maybe made complicated with the scenario where you have to, based on the criteria, maybe you want to distribute the number of nodes and then see how much time it is needing altogether. For example, I'm just thinking aloud live, uh, some type of problem like this. Let's say I say that, okay, I already said it has 200 computing nodes with 120 GB RAM, and hmm, okay, and then criteria is this. Um, let's say, uh, let's say you launch a program. You launch a program. Your program, let's say, takes, okay, this example 230 GB. Okay, and you find that a machine, let's say, change this number to let's say 25 gig, 25 gig, and then at that point you will see, you find that, okay, all the nodes has 25 gigabyte available per node. So what, from these, what we can deduce is that number of nodes I am going to need for my problem is this, uh, like 230 divided by 25, number of nodes, which is about 230 divided by 25, 9.2, but 9.2 is uh, is an odd number, so it is like a ceiling of these 10 nodes. Okay, and now let's say, yeah, and let's say now you say that these nodes has average access time. Let's say I give you some table, like node 1 is maybe average access time is 180, node 2 is 150, node 3 is 189, etc., etc. Let's say I give you a table like this, that is the average access time per node, and I say that this program running on this local node has equal possibilities to access this node for 1 million access. So 1 million access, that means we are looking for the 10 nodes, and out of these 10 nodes, each node has 0.1 probability to be accessed, right? So that means out of that, your 9 of them would be remote. So out of these 10, 1 is local and 9 is remote. Then you need to calculate based on these time given, average access time given, you need to compute your distribution. So that kind of problem can be given always. I mean, you can think of more complex problems. So basically based on the number of node availability and how much distribution you can make towards that node.
Okay, that makes sense. Thank you.
All right. So what else? Is there any other question? No? Okay, I don't have many things for you tonight to discuss about or pointed about. I hope you guys reviewed the videos and lecture notes. And what else? Wednesday is a holiday, all you know, no class, no office hour. It's a Veterans Day. So next time I'll see you on Monday. Any question on the project side? Project is going okay, smooth?
I had a question not about the project, but is there no quiz for this module?
No quiz of what?
No pop quiz because there's no class on Wednesday.
Pop quiz can come up anytime. Come on.
Oh yeah, of course. No, that was just funny.
Yeah, yeah, definitely. Yeah, you can expect some pop quiz to come up here and there regarding this module. So yeah.
Okay, good to know.
Sorry, Professor. Can you actually explain again the problem that you just made up in a Jamboard?
Oh,
the one in blue. Yeah.
Mm-hmm. So it's telling about this. Let me share the screen. It is all telling about these. Each of this node has 25 gigabyte available. So that's your constraint. Okay. And then you have 230 gigabyte of machine, like you need that memory, right? So point become then how much memory or how many processes you can send it to, right? So that's why we determined that we have like 10 nodes needed, and then we say that each node is distributed node. This process can access memory from each of these nodes equally likely. So that means we are distributing over 10 nodes of the entire memory. 230 gigabyte memory is being split over 10 different machines. And each of these machine is accessed, including the local one, where the process is running, including the local one. Equally likely it is hitting them. So probability is 0.1 for accessing from different nodes. And then I give you a table that my access time from node 1 is 180, 150, like heterogeneous access time. It can depend on the machine load, depend on the network communication capability and all this stuff. So it may not have same amount of access time or uniform amount of access time, remote access time. So I give you a table. So based on that table, you need to come up with the how much total access time it needs. So this problem, the earlier problem was more like a uniform. It's saying uniformly it is 180 nanosecond of access time. And it didn't even talk about how many nodes it is. It didn't need to, how many nodes it is distributed, because it already came up with a probability of remote access and so on and so forth. But the other problem, the more complex problem is also you need to come up with the probability of accessing of each of these node, and then combine the access time with that probability and to come up with the total time. So that's the difference of this problem in the blue with the original one. Is that clear, Catherine?
Yeah, so in the blue one, the answer is like, oh yeah, so which one is the answer?
No, we haven't come up with the answer. I'm just giving an
Oh, okay. Oh, okay, okay. All right, thanks.
Yeah, just build up your own problem. And let's see who can send me interesting problem. How about that? In that nature.
Professor?
Kevin.
So for this problem, you have the 128 gigabytes, and you also have the local memory occupancy as 25 gigabytes. So does the local memory occupancy refer to the amount of RAM for each node? Like here you use like you have 0.230 like terabytes divided by 25, which is supposed to be like the amount of terabytes also. Like
So this is okay. So this is saying that okay, each node has 128. Okay,
Mhm.
gigabyte RAM, but the constant saying that all the node has 25 gigabyte available. Maybe the other processes are running there.
Okay, oh, that makes
So
sense.
all of them are running different other process. So when you requested resource, it seems like each of these node can offer you only 25 gigabyte. Okay, so under that condition, how your process is distributed. So you must create like a 10 processes out of that. So this is like kind of a dynamically resource allocation technique. So when you're running this software or implementing this software and analyzing the available resources with the constant and everything, your program is intelligent enough to see, hey, okay, under this condition, I can maximum go like 10-way parallelism. So I create 10 sub processes and send it to the cluster nodes. Okay, something like that. Or in this case, it is more like a memory oriented. In this case, it would be like, okay, I am creating a sub process. I need 230 gigabyte of memory, but each of this individual machine, I can only get up to 25 gigabyte. That means my data has to be coming across 10 different machines for me to work with. So that's what I'm determining here at this point. Make sense, Kevin?
Yeah, that makes sense. Thank you.
Okay, what else? No? Is there a quiz this weekend? Let me see.
There's one on Friday.
Yeah. November 13th, right? 13, 14. Yeah, this weekend. Yep. So make sure you also complete the quiz this weekend and work on your project. You keep on writing the report in parallel. Very important. Okay. So has anyone come up with that parameterized flip-flop I was talking about last class? I remember something we talked about. Like for the program counter and stack pointer to be resetted with a like specific values. How can we implement it? Oh, probably most of you haven't reached that point yet. So yeah, we'll keep discussing on that line as well once we hit it. Okay then, all right. Good night, everybody. Let's close this class this time and we'll see you on next week then.